Pianos are tuned in the equal temperament system. Now, how do we arrive at these pitches? The theoretical pitch of each respective note is its lower neighbor times the 12th root of 2. That's 1.059463. So, for instance, A220 times the 12th root of 2 is 233.08. Now, if you keep multiplying each respective pitch in the chromatic scale by the 12th root of 2 12 times, you get to the octave A440. So that's where that 12th root of 2 thing comes from. You keep multiplying something by the 12th root of 2 12 times, and you get twice the original number. So you spread that idea all over the keyboard, and you get the theoretical pitches of all 88 notes. By the way, there's a reason I use the word theoretical, and I'll talk about that another time. So how does a piano tuner tune equal temperament? He either uses a fancy electronic device, which also we'll talk about in another time, or he does it the old-fashioned way, which is using the principle of beats. No, not these beats. The deal with beats is kind of like an acoustical Mourier effect. Like, say I had two picket fences. Same length, but say one has 50 pickets and the other has 51 pickets. And if we superimpose them, you see a pattern that changes from gray to white to gray over its distance. So an analogous thing happens in sound. Say you have two tones, one is at 220 cycles per second and the other is at 221. Over the course of 1 second, the peaks and the crests of these waveforms will enforce and cancel each other out. Here's what that would sound like. So if a tuner wants to tune a unison, like two strings in one note that are supposed to be identical, he tunes them so that the beat slows down and disappears. The beat gets slower as the two tones get closer together. Okay, now back to equal temperament. How does one use the principle of beats to tune all the pitches? So let's assume for right now we've tuned our A220 correctly, and we know the E, the fifth above that, is supposed to be 329.63 cycles per second in equal temperament. Remember how that is a little bit different from the perfectly harmonic fifth? When we play the A and the E together, we listen for the third harmonic of the A and the second harmonic of the E. We call that the coincident harmonic. In the perfectly harmonic world, they would be identical. In equal temperament, they are just a little bit different. In fact, they're different by 0.74 cycles per second, and that's the beat we should hear. Here's a pure tone version. See if you can hear that in the piano notes. Now the same type of thing happens with the third. The thirds have a coincident harmonic at the fourth harmonic of the lower note and the third harmonic of the upper note. Remember how the thirds are more incorrect harmonically from the fifths? And that's reflected in the fact that the beat speed associated with thirds is pretty fast compared to the fifths. So this is basically what a tuner is doing most of the time, listening for beats, adjusting the pitches, getting the beats right, getting the intervals right. Now the quality of this recording may not be good enough for you to actually hear that, and sometimes it's actually hard to hear at the piano itself. Sometimes you have to move your head around in order to hear the beat that you're trying to hear, and oftentimes there's other beats going on, there's other kinds of unusual noises happening in the piano. And it takes a while to actually hear, to focus in on the beat that you're trying to hear. In the case of octaves, all their coincident partials line up perfectly. So octaves should be tuned to be beatless, theoretically. Now we can use that beat thing that we learned from the thirds as kind of a helper. In our 220 to 440 octave, the F below the A should produce a beat, a major third, which is the same as the 10th it produces with the A440. Sometimes using this type of test is very useful in many different situations because you can discern that beat pretty well. In fact, if you're trying to tune the octave, it doesn't really matter if that third below is perfectly tuned because you're just using it as kind of a test thing to see if the beats are the same, to see if that octave is right. So back to the thirds, the beat rate of that F to A major third is 6.9. As you go up the keyboard, since pitches get higher, so do the beat rates. One of the tools that a tuner uses is what's called the ladder of thirds, where each successive beat rate is faster. So when you tune the F to the A, and then the A to the C sharp, and then C sharp to the F, and that F to the A again, you have 4 of these thirds. Each successive one beats a little bit faster than the one below it. By the way, sometimes people ask me if piano tuners have absolute pitch, and I say, well, not necessarily, but we are pretty good at pulling a metronome tempo out of the air because of all this beat counting we do all the time. Because of this business of coincident harmonics, pretty much every interval you can name has an associated beat rate. Like our A220, the major third above it is about 8.7, the fifth above it is about 0.7, the fourth above it is about 1.2, the major third below it, 6.9, the major sixth above it, 9.3, the minor third, about 11.4, and so on and so forth, yada, yada, yada. An experienced piano tuner knows all these beat rates, just like an experienced singer can sing any interval pretty much automatically, hardly even thinking about it. Now, if this all seems pretty complicated, like a Rubik's Cube, just wait till part 3.